Hi, a pleasant day to all. Today, we will continue our topic on materials and engineering. And for this session, we will cover the ceramic crystal structures. All right, let's start. Okay, so for this lecture, we need to review cations versus anions. And also the magnitude of electrical charge, the relative sizes of cations and anions. So here you can see um, cations and anions here. So we can see the relative sizes of these cations and anions. So there are bigger cations, medium one, and the small ones. So if you recall in lecture 4-1, ionic bonding is predominant in ceramics. I hope you still remember that one. Thus, we will be dealing with anions and cations for the duration of this lecture. So recall that your cations are the positive ions and your anions are the negative ions. And we also have magnitude of electrical charge. So for say we have a cation X with a charge of A plus or A positive, and an ion Y with a charge of B negative. The resulting ionic compound would be written as X sub B, Y sub A. So how does this happen? So let's write a chemical equation for us to be able to easily grasp how chemical equations are written, especially in for ceramic crystal structures. So we have, say, cation X with a charge of A plus. Then you have your anion Y with a charge of B minus. So notice that your charge transferred to, you just need to copy the charge and then make it as your subscript. So say for X, then you have a subscript of B as, yes, a B. So you have X sub B, and then your A plus here, it becomes your subscript of your Y. So that's why you have X sub B, Y sub A. So you can break down these two compounds into the respective cations. So for this one, say for example, calcium fluoride. So if you need to break down this one to its respective cations and anions, you can follow the same way here. So say you have your CaF2. So your if you need to break down the cations and anions, so you have Ca plus your F or your fluoride. But the question is, what is the charge of your calcium and the charge of your fluoride? Of course, you can verify that one in your periodic table, but say there's no periodic table and you are in a hurry, so you can just write it. You can just follow how chemical equations are written, especially in chemical ceramic structure, ceramic materials. So here we have Ca calcium fluoride. So you will know that your calcium has a +2 and your fluoride has a +1. Kaya nag-exchange lang muna sila. So Ca 2 plus and your fluoride is your has a charge of -1. Of course, sodium chloride is very easy. You have +1 and -1 charges of your cation and anions. Okay, so relative sizes of cations and anions. So we will denote cations as blue circles or sphere, and your anions are the red ones or the red circles or sphere. So take note that these cations and anions has also a radius. So we will denote cation radius as R sub C and your anion radius as R sub A. Also in ceramic crystal structure, we do have coordination number. So it is coordination number is closely related to the cation and ion radius ratio. That is your R sub C over R sub A. So here for this figure, the ratio or the cation and ion ratio, this one is less than 0.155. This one is around 0.155 to 0.225. For this figure, you have 0.225 to 0.414. And for this one, you have 0.414 to 0.732. And for this one, you have 0.732 to 1. And notice that your CN for this one is, or the coordination number is 2, 3, 4. You have 1, 2, 3, 4, 5, 6. And this one is 1, 2, 3, 4, 5, 6, 7, 8. So you have 8. Okay, so the closer the radius of the cation, the closer the radius of the cation is to the radius of the anion, the more anions are needed for the compound to be stabilized, just like this one. So this is very small. So you only have you just need 2 anions. But for this one, you need 8 for this figure. So in other words, the closer the ratio R sub C over R sub A to 1, which is in this case for this figure, the bigger the coordination number. So notice you have 2, 3, 4, 5, 6, 7, 8. So this is, you have a bigger coordination number if the ratio is closer to 1. Most ceramics exhibit one of the 3 most common ceramic crystal structures. So what are these? So we have AX type, we have AMXP type, we have the AMBNXP type. So this AX type, usually common ones are ceramic structure that exhibit this one is a rock salt structure. So the very famous one is rock salt is your sodium chloride, an example of this. There are also other compound that exhibits this AX type, like magnesium oxide or your ferric oxide. So the rock salt crystal structure is basically two interpenetrating FCC lattice. So for one cations, another for one anions. So for sure, if you recall with our previous lecture, we are introduced to face-centered cubic. So this is very familiar one. So here, it was the rock salt crystal structure is basically two interpenetrating face-centered cubic lattice. So the blue ones is for your anions, and the red one is for your cations. So first cubic, and then there's interpenetrating another face-centered cubic for your anions, for your cation. So you have formed a salt crystal structure. Cesium chloride is also an example of AX type. The cesium chloride crystal structure looks like a BCC lattice, but it's similar, but actually it's not, since the atom at the center of the unit cell is another element. So this is the chloride, the cesium. So it's almost the same, but for this example, AX type cesium chloride structure, it's not actually a BCC type. It's just similar because the atom at the center of the unit cell is another element, which is in this case a cesium. All right, so we also have zinc blended structure. So we have your sulfur here, sulfur atoms, and you have your Zn, the blue one. Also, it also adapt the same type is a silicon carbon or carbide. Okay, so in ceramic crystal structure, we also need to know the density because that's very important property as well. So therefore, we need to compute the density. So for ceramics, we have this formula. So theoretical density, that is in grams per cubic cm. So we have your n prime, that is the number of formula units in unit cell or atoms, and then your summation of your A sub C, that is the sum of atomic weights of all cations in formula unit, that is in grams per mole. And we also have the summation of your A sub A, that is the sum of atomic weights of all anions in the formula unit, also in grams per mole. And your VC, that is your volume of unit cell in cubic centimeter. And lastly, your Na, that is your Avogadro's number or your Avogadro's constant, that is in atoms per mole. That is 6.022 times 10 to the 23. That is the Avogadro's constant in atoms per mole. Okay, so the formula is just an expanded version. This one is just an expanded version for the metallic crystal structure that we have presented in our previous lecture. For us to appreciate this formula, we will have an example. So we are tasked to compute the density. So we have here sodium ion has an ionic radius of 0.102 nanometer, and a chloride ion has an ionic radius of 0.18 nanometer, and then your NaCl maintains the rock salt crystal structure, and the atomic weights of your Na and your chloride are 22.99 grams per mole and 35.45 grams per mole, respectively. So you are tasked to compute the theoretical density. Okay, so this is the structure of your sodium chloride, a rock salt structure that we have presented earlier. So let's zoom in into this structure. So think of the FCC unit cell, but with additional sodium ions in red that is enters spheres between the chloride ions. So let's add this one. So here we have now the sodium enters spheres as between the chloride ions. Okay, so let's recall the equation of density. So recall that the equation of density is we have this n prime that times the summation of your atomic weight of your cations, and also the summation of atomic weight of your cations or anions, all over your VC times your Avogadro's number. So let's find first the n prime. So let us count the formula units, or how many sodium chloride or NaCl molecules there are in one unit cell. So knowing that these are two FCC unit cells, they should have the same number of atoms. That is 4. So here, this is half an atom for each of the 6 bases of the cubes of 1, 2, 3, 4, 5, 6 at the back. So you have for this one, this is 1/8 of an atom for each of the 8 corners of the cubes of 1, 2, 3, 4, 5, 6. Sorry, again. So 1, 2, 3, 4, 5, 6, 7, 8. So that's why you have the 8 corners of the cube. So your N for your Cl, you have, if you will count that one, you have 6 times 1/2, because this is 1/2, plus your 8 corners times 1/8 of an atom. So therefore you have 4 atoms of your Cl or your chloride. Then we also need to look for the sodium or the Na. So this is 1/4 of an atom for each of the 12 sides of the cube. So we have 1/4 times 12. This one at the center, this one is the whole atom at the center of the cube. So that is why you have 12 times 1/4 plus 1 times 1. So 12, where this, why 12? So you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you have 1/4 times 12 plus this one is 1 whole atom at the center of the cube. So that is 1 times 1. So therefore, you have your total atoms of your Na is equal to 4 atoms. Okay, so if you will write it this way, so you have 4 Na um, plus your 4 Cl minus is equal to 4 NaCl. So your N prime is 4 atoms for your NaCl. So N prime that we're looking for is the um, um, number of NaCl molecules, not just the Na or not just the chloride, but it's the NaCl molecules. There are in one unit cell. So therefore, you have 4 atoms of your NaC, 4 atoms of your NaCl. For your the summation of your A sub C plus summation of your A sub A, this one, let us add that. Let us just add the atomic weights of all cations and anions for one formula cell, for one formula unit. So it's very easy. We are already given with the atomic weight of your sodium as well as for your chloride. So we are given with 22.99 for your sodium and 35.45 for your chloride. So therefore, you have 58.44 grams per mole. So check N prime. This one is we have already identified, which is 58.44. So check. So we need to look for VC as well. So for a cubic unit cell, the volume V sub C is the cube of one length of a side of A. So your VC is just equal to A cube. So if this is your A, the length of one side of a unit cell, then this portion is the radius of your chloride, and the other one also radius of your chloride. But this one is the diameter or the radius. The two, you just need to multiply 2 with the radius of your Na. So you have that one. So therefore, if you will express A in terms of R sub your R radius of your chloride or radius of your sodium, you can write it this way. So you have 2 radius of your chloride, because you have 2 1 and there's under 1 here, plus 2 RNA, that is the radius of your sodium. We are given with the radius of your chloride given in the problem, that is 0.181 in nanometer, and the radius of your Na or your sodium, that is equal to 0.102 in nanometer also. Converting it to centimeter, the radius of your chloride is 0.00000 again 0.0000001 times 181. So for you to be able to easily type this one or write this one, you can make use of scientific notation. Nanometer is times 10 to the negative 9. So you can just write it in that manner. That is also acceptable. But for the sake of illustration, I just write it in 0.00000000181. Same with the radius of your sodium. All right, so substituting the number of your the radius of your chloride and the radius of your sodium, then your A is equal to 0.00000000566 cm. Then take the cube of it. So you have now the value of your V sub C is 1.0 813 times 10 to the negative 22 cm cube. So we have the n prime. We have the summation of a sub c plus your a sub a, and then your VC. Lastly, we will use the Avogadro's number for us to be able to compute the density, the theoretical density. Avogadro's number is equal to constant is equal to 6.022 times 10 to the 23 atoms per mole. Using that one, substituting all the values, you have your n prime, your summation of your atomic weights, and then you have your volume of your unit cell, and then your Avogadro's number, Avogadro's constant. Then canceling the units, and the remaining units is in grams per cubic centimeter. So you now have the density, which is equal to 2.14 in grams per cubic centimeter. So this is what we have computed. Then let's compare it to the literature. The value for the density of table salt is 2.16 grams per cubic centimeter, which is not far from the value that we have computed. Okay, so let's move on. So a group of ceramics worth noting are silicate ceramics. These are ceramics composed of silicon and oxygen. So they are called silicate ceramics. So one is silica. This is the structure of silica. Silica, and then it is the simplest silicate material with a formula of SiO2 following a crystalline structure. Another one is the silica glasses. So if you notice, it's almost the same, but wait, there's more. So here, silica glasses are non-crystalline. This means they are amorphous, and they are usually used in windows and containers, etc., etc. So notice that there is an added atom here. So adding intermediate darker colored circle, as you notice, it lowers the melting point and viscosity of glass, making it easier to be shaped and formed as desired. So that is why some manufacturers favored glass, because it's easier to shape and form as desired according to their needs, or according to their specification that the company is needing. All right, another one is silicates. So silicates, there are different types of silicates. You have SiO4, Si2O7, Si3O9, Si6O18, and SiO3, and to the nth level. So those are your silicate ceramics. One group that there's another group that doesn't fall within any of the three traditional classifications, and these are the carbon structures. So carbon, there's a different form of carbon material. Another a very famous one is graphite, and this is one of the most common carbon structures, and is sometimes classified as ceramics. Of course, the most valuable, should I say, one of the most valuable material, that is a diamond. So this is the structure of a diamond. A diamond is a cubic crystal structure. Uh, looks uh, looks a lot like a zinc blende structure that we have presented earlier. The difference is that all atoms involved here are carbons. So all atoms are carbons. There's no other elements here. So this is a diamond crystal structure. Okay, so showing here the graphite structure. So graphite, this is the a graphite material, or a graphite that you can find. Actually, I haven't seen a graphite personally, but you can search online on figures of graphite. So this is a graphite, and this is the structure of the graphite. Also, there is a what we call fullerene, and it has a structure like this. So fullerene is a composed of 60 carbon atoms, where carbon atoms are connected in hexagons and pentagons, where no two pentagons share the same side. So this is fullerene. Okay, so I think that's all for our topic this day. So see you in our next topic, and have a good day. Bye.